I'm going to talk today about the atmospheres of Uranus and Neptune, and you can see here two of the best images that were obtained by the Voyager 2 spacecraft flyby in the 90s. So there you see Uranus on the left, Neptune on the right, two worlds that are very much highly unknown because we only have close data from this mission from Voyager 2 and we have never had a full mission dedicated to these planets. So the outline of my talk today will be given in 3 parts. I will be talking about the planetary context of Uranus and Neptune, which are their main characteristics, why they are important, and one of the reasons they are important is because they are serving as a bridge to understand some very common exoplanets. I will be also showing that there are key questions, important questions related to their interior and composition. And although these are topics that are not related normally with atmosphere dynamics, in the case of Uranus and Neptune, they are involved because the behavior of the atmosphere depends on the chemical composition of the atmospheres, which in turn give us hints about how these planets were formed. So there are important connections between planetary formation and atmosphere dynamics in worlds like Uranus and Neptune. I will dedicate most of the talk to describe the atmospheres, general properties, how the winds are, which are the heat sources, what are the clouds and weather systems that we can see in images like this. So these images are also obtained by Voyager 2, but these are modern processing of the data. And you can see plenty of details here in Uranus, where at the time of the Voyager 2, the images looked blunt. With modern processing, you can get lots and lots of atmospheric details and lots of structures in this highly unknown atmosphere. And the same for Neptune, in which you can also see increased details. Then I will be deepening into the atmosphere in the lower parts that we cannot observe directly. And I will be talking about moist convection, which serves as an important, where we have important problems related with how moist convection works in an atmosphere made of hydrogen and helium with condensators like methane, which is much heavier than this very light species. Then I will summarize some of the uniqueness of Uranus and Neptune. And then in the last part, I will be speaking about modern observations of these planets, the very near future, and the possibility to develop future missions to explore these icy giants and really know about them with a dedicated space mission in the future. So these are again the 2 planets visited in 86 and 89 by the Voyager 2 in short flybys. They are the planets that orbit the Sun at the largest distance. So Uranus and Neptune are orbiting the Sun at a distance of 20 and 30 astronomical units, 20 times farther away from the Sun and the Earth, and 30 times farther away to the Sun than the Earth. So the orbits are very slow. The period of a year in Uranus is 84 terrestrial years, and in Neptune is 165 years. And both planets have the axial tilt inclined, so there are strong seasonal effects that evolve in very long time scales. Because they are so far away from the Sun, the atmosphere are very cold. If you were to measure the temperatures at 1 bar, you would measure temperatures on the order of 70 to 80 Kelvin. And these are giant planets, but not so large as Jupiter and Saturn. They are about 15 Earth masses, and their size is about 4 times the size of the Earth in terms of the weight of the planet. Both Uranus and Neptune have fast rotations, so they have a daily period of about 17 hours, and this means that their atmospheres are going to be in geostrophic balance, verifying the geostrophic balance, in which we are going to find sonar winds in the directions of the parallels, and also we are going to find atmospheric features like close vortices, like this one here in this image of Neptune, which is known as the Great Dark Spot in Neptune that was observed in 1989. And these dark spots are somehow mysterious even now, decades after the discovery of the first of them. The interesting thing about these atmospheres is that the planets, they are themselves made of ices. So when the solar system was young, there were lots of ices in the outer solar system, water ice, methane ice, ammonia, and different ices that combined together to form large protoplanets. And these protoplanets were massive enough to accrete hydrogen and helium. And so Uranus and Neptune are surrounded by envelopes, atmospheric envelopes of about 5,000 kilometers in size, so about a fourth time of the radii of the planet is these extended atmospheres of hydrogen and helium. But in these atmospheres, there are lots and lots of condensators, gases that come from the lower part of the atmosphere, from these ices. And we think that the amount of atmospheric volatiles in these atmospheres is very large. If you compare the chemical composition of the atmosphere with the chemical composition of the sun, these planets are enriched 20 times or 50 times more than the sun, or even 80 times. And this is several tens of times the enrichments in heavy volatiles than what we find in Jupiter and Saturn. And because all of these condensates that are able to form clouds are very abundant, and they are much heavier than hydrogen and helium, these atmospheres are in a completely different regime regarding their vertical equilibrium and the ability to develop moist convection. And this is going to be very critical in the study of the features that we are observing here in these atmospheres. If I were to summarize the characteristics of the planets, they are here. Uranus is a quiet planet in which the atmosphere evolves very slowly. We don't have lots of atmospheric details, they evolve very slowly. But Neptune is very active. Even though it is farther away from the sun, these clouds change continuously, very, very rapidly. The planetary amount of clouds changes from one year to the other. And of course, there are other intriguing questions about the satellites that I will not be talking about today. One of the main motivations to study these planets is because in the very large population of exoplanets that is known to us now, planets with the size of Uranus and Neptune make the biggest part. This is about 50% of all of the exoplanets that we know have masses that are similar to Uranus and Neptune. And many of these planets are going to be very, very different. Even Uranus and Neptune could be intrinsically very different, although they share the characteristics that I showed it before. So we want to study Uranus and Neptune to better understand the exoplanets as a whole. How are these planets formed? Why are they so numerous? What are the physical properties, and how their atmospheres are going to behave? And of course, to understand how these planets form, we need to have a good understanding of the chemical composition, and we need to go inside the atmosphere and measure the components of the atmosphere in a way similar to what the Galileo probe made in Jupiter in 1995. When the Galileo probe entered into Jupiter, it found an atmosphere made of hydrogen and helium, in which volatiles like oxygen, which makes water, or nitrogen, which makes ammonia, or carbon, which makes methane, were enriched. For water, it was not enriched. There was a mystery of missing water. This is because of the local meteorology that occur at the location where Galileo entered. But also there were other chemical elements like krypton, argon, and xenon, noble gases that are enriched. And in Saturn, we don't have a probe, but we have spectroscopic measurements that tell us that they are enriched in these heavy elements. And carbon is going to make methane, which is not going to condense in Saturn. But in Uranus and Neptune, we expect that the volatiles are going to be much, much more abundant, so tens of times more abundant than in Jupiter. And these are the only measurements that we have for carbon in the form of methane. And we are going to have lots of different condensators that are going to be deep inside the atmosphere, and they are going to shape how these atmospheres work in a very different way to what we observe in Jupiter and Saturn, because this enrichment in heavy molecules are tens of times larger in Uranus and Neptune. If we go into the atmospheres, these plots highlight the extended atmosphere of hydrogen and helium here in gray, and the interior, which is mostly unknown, with the ices, maybe rocks inside, and these planets, they have this chemical composition, but they could be mixed, and we could have mixed interiors, and we really need to understand these kind of things. And we have mixed interiors, we may have even larger amounts of condensables in the upper atmosphere, changing the way the atmosphere is behaving and changing the way the atmospheric systems that we are observing are going to happen and to behave. If we want to observe the planets, we can go to the old images by the Voyagers, here in green, and see how these planets look like, and the clouds. These planets are so cold that all of the clouds that we are seeing here are made of methane condensing at these temperatures of about 80 Kelvin. With modern technology, we can make, with telescopes using adaptive optics, fantastic observations of these planets. And so here you have Uranus, again, Uranus in the upper row, Neptune in the lower row, with lots of different atmospheric features that, however, evolve very, very slowly in Uranus, but they change very, very rapidly in Neptune. And of course, we can also observe with the Hubble Space Telescope, in which we can go to shorter wavelengths, to the blue wavelengths, in which we are sampling higher in the atmosphere, and we can also sample a little bit lower, and we can see these deeper clouds, these dark spots, these storms, and all of this variability in these atmospheres. So this is one of the poles of Uranus and changes in seasons as the planet is rotating. And the difficulty to understand these planets is that they are very small when you are observing them from the ground or from the space with a telescope like Hubble. Uranus is only 3.7 arc seconds observed from Earth. Neptune is only 2.2. If we were to compare this with Jupiter, Jupiter can be about 45 arc seconds in size. And so we have a great difficulty to get observations with spatial resolution enough to get information about the atmosphere dynamics of Uranus and Neptune. The axes of rotation are tilted, the seasons are long, the insolation in the planet changes a lot. This is going to change the upper atmosphere in time scales of decades. But because these planets have massive atmospheres, if we go slightly deeper in the atmosphere to the level where we are observing these clouds, close to 1 bar, the thermal constant at these levels is very large. And so we are not expecting to observe very strong changes at depth in these planets, but we are going to see changes in the upper phases and in the behavior of the upper atmosphere. Here, in these plots, you are seeing also dates. When Voyager observed these planets, and we were observing mainly the south hemisphere with Voyager, and now with the James Webb, we are observing mainly the north atmosphere of Uranus, the northern pole. And if we develop a space mission in the next few decades, we will be seeing changes in the seasons in these planets, depending if we arrive there in the 2040s or in the 2050s. And the same for Neptune, but of course in Neptune with longer seasons, with a year of 165 Earth years, things change very, very slowly in Neptune in terms of the different seasons. If we want to study the behavior of these atmospheres, we need to have information about the temperatures. These are thermal profiles obtained by experiments of radio occultations in which you can measure the density of the atmosphere, and from that density measure the temperature. For Uranus in green and Neptune in blue. These are kind of unique data that was obtained by Voyager 2. You see that although Neptune is much farther away from the Sun, the thermal profiles are very similar, and that is because Neptune has an internal heat source. Uranus receives about 3.5 watts per square meter from the Sun. Neptune receives about 1.5 watts per square meters from the Sun, but it also has an inner heat source from residual heating from the interior, maybe heating that is being released now after a giant impact in the past, and it amounts to 0.3 watts per square meter. And this is interesting because this means that this atmosphere is heated from below and from the upper part in a, let's say, close manner. And in Uranus, it's only from the Sun, but the dynamics of both atmospheres are similar. We know this because of the differences in the temperature equilibrium of the atmosphere and the effective temperature in which we are observing the radiation coming from these planets. In both planets, we have solar winds. We have fast rotation, geostrophic equilibrium, solar winds, and these solar winds are very, very fast. Although we have these very small amounts of energy coming to the planets, Neptune is the planet with the fastest wind jets in the solar system, 400 meters per second to the west. Uranus is slower, and then we have these middle latitude jets. And this is very, very different to what we observe in Jupiter and Saturn, in which we have these complex multi-jet systems, which are not so intense, but they change a lot from latitude to latitude. These solar winds correspond to data obtained from the Voyagers, and more the data obtained from ground-based large telescopes with 8-9 meters size, with adaptive optics observing the motions of cloud features. If you look at panel B, is Neptune, and there's a lot of noise in these measurements. And in panel C is again Neptune, and different wind profiles obtained at different depths if you observe at different wavelengths, and lots of variations and structures that change a lot in winds. These are changes of hundreds of meters per second. We believe this is due to vertical wind shear that we are not able to study correctly. And if you look at this, the highest wind shear is in the equator, where thermal winds are not possible to, the thermal winds equation is not going to work, and you need a different kind of regime. Another thing that makes interesting Uranus and Neptune is that thermal winds are different in these planets. Of course, if you have geostrophic winds, you have the thermal wind relation in which a meridional gradient of temperature is going to change the way the solar winds are changed in vertical. So the vertical gradient of solar wind in terms of pressure depends on the meridional temperature gradient. But because we have different compositions related with the amount of condensators that can have at different latitudes, if you have different amounts of methane at different latitudes, you are also going to have an additional term here modifying the thermal wind, and this is called the humidity wind. If you want to study how winds change in altitude, you need to measure temperatures and you need to measure abundance of condensators, and this is difficult. If you want to study the thermal, this thermal wind relation in the equator and explain this 200 meters per second difference in these wind measurements, then you need different kinds of approximations. And this is one that has been developed recently to try to study this problem, where thermal winds are corrected. And here you have the gradient in pressure of temperature and in composition to try to be able to understand better this kind of vertical gradient in the equator of Neptune. If you compare these icy giants, Uranus and Neptune, with Jupiter and Saturn, the atmospheres look different. The winds are very different, as you can see here. So this is Jupiter, this is Saturn. These are Uranus and Neptune, with much farther, more intense winds in Neptune. And this problem with the variation of the winds and the vertical winds here, we don't have that kind of data for Uranus. We don't know what is happening there in Uranus, but you see that there are lots of stratospheres and waves. We can go a little bit deeper into the atmosphere, observing in the millimeter and in the radio wavelengths the thermal radiation escaping from these planets at millimeter and micrometer wavelengths. And in order to do that, you need to use radio telescopes like the VLT or ALMA, and these are maps of, I think this is Neptune, from ALMA in different frequencies, in which you can see a structure that goes deep into the atmospheres to level much deeper than these high cloud tops. These are about, let's say, 1 bar, and these maps correspond to tens of bars below the atmosphere. And if you want to understand this, you can start to think about meridional circulations different at different depths to try to explain this kind of observations and the variations in abundance of condensators that we find in these planets. So lots of things that we need to study, and you see that the data does not resolve with enough spatial resolution these planets to really understand what is happening. So these are just first approaches to understand the dynamics of these distant worlds. If we focus on Uranus, these are images of Uranus from the Voyager, the best image obtained by Voyager, processed with the technology at the time of the late 80s, and then modern processing of those data in a recent paper by Ricardo in the United States, in which he basically uses different images obtained in different times, compensates for the rotation of the planet, accumulates the images, and so he gets a high sign to noise rate image that he can further process, and so he can see the very faint scale structure and the small scale features here. And if you do the same with observations in adaptive optics from the ground, observing from hours and compensating from the planet rotation, then you can make images like this, convection in the South Pole region, waves in the equator, complex waves, possibly related with mostly equatorial waves, and the appearance of different clouds on different years as the spring arrives to these latitudes, and we start to develop moist convection in the methane condensation layer. Most of the clouds that you are observing here are methane. Some of them are active, but some of them are very high in the atmosphere. They correspond mainly to hazes. It's difficult to prove that these are really strong storms. Most of the things that we are observing here is the development of hazes in the upper atmosphere, with only a few of them that can be really signaling a strong moist convection, even though here we are in the springtime and we are seeing how the atmosphere is reacting to the change in the seasons. Neptune is very interesting because it has these unique features, these great dark spots. This is the first one that was observed by Voyager. You can see here these high clouds in white and low clouds deeper in the atmosphere in dark blue. This is deep in the atmosphere and the dark clouds are deeper. So these are maybe not methane clouds, the deep clouds that we are observing here. These could be related with different layers of clouds that are deep into the atmosphere, in this case, hydrosulfur, H2S, condensing at a pressure of about 10 bars in the atmosphere of Neptune. And here we have these high clouds, methane, that are formed when you have a mass of air that is coming above an obstacle, in this case, this anticyclone, and then it condenses and forms these companion clouds. And this was the first of these dark spots that was observed in the year 1989. But in the last years, we have been observing this kind of dark spots in different locations of the planet, here in different years, in different locations. And because the solar winds change very, very smoothly from one latitude to the other, these giant vortices can migrate in latitude. If you have a dark spot like this, it's going to migrate to the equator, where the Coriolis forces are going to change. And the models predict that this kind of vortices, as they migrate towards the equator, they should be destroyed and they should produce new clouds features here that we have never been able to observe. There have been a few attempts, not only with the one dark spot that was discovered in 2018 that has been moving to the equator but has never really broken apart and disappeared. But models are able to predict how these vortices can migrate in agreement with the observations. So again, these are different views of different dark spots. The biggest one, or the best one that we observed with the Voyager in 1889, and some of the most recent ones. This is the one that is active currently in the north hemisphere of Neptune. And because these dark spots are only observable in short wavelengths, we can only observe them with Hubble. It's very, very difficult to observe these dark spots with adaptive optics. The VLT, the 8.5 meter telescopes in Chile, with some adaptive optics and some instruments, sometimes have been able to observe some signatures of these dark spots, but this is tremendously difficult, and generally most of these observations of dark spots correspond to Hubble. And as I said, these are interesting because they are sampling a different level of the atmosphere at 10, 12 or 13 bars instead of 1 bar, which we are observing here in the method. So here are different instances of dark spots that have been observed in different years with different sizes. These are huge features with sizes of thousands of kilometers. They meridionally drift. They have oscillations in shape, in size. The Coriolis force is different in different locations, and these are the predictions of the kind of wind speeds, the sonar velocities, the tangent velocities that they should have to be in equilibrium. But we have never been able to measure those winds inside these dark spots. And approximately, we observe one of these dark spots every 4 or 6 years. Another interesting thing of Uranus and Neptune is that if you want to study what is happening below the upper clouds, the atmosphere is very cold. It's made mainly by hydrogen, and hydrogen has a particular thermodynamics. There are 2 states of hydrogen at low temperatures. If you have a molecule of hydrogen, the spin of the protons are important. You can have 2 states with parallel spins of the protons or anti-parallel, and then you are going to have autohydrogen or parahydrogen, and the transitions between these 2 species of hydrogen are forbidden in quantum mechanics, and they can only transform one to another when there are collisions with particles. So this means that once you have a particular distribution of auto and parahydrogen, it's going to stay there for a long time until these hydrogens equilibrate to a particular temperature. And the thermodynamics of hydrogen, of autohydrogen and parahydrogen, depend on temperature. If you are at low temperatures, auto and parahydrogen have different specific heats. If you are observing the upper atmosphere and you want to see what is happening below, and you want to define how your atmosphere, how far is from adiabatic conditions or how close, you need to take into account which is the state of the hydrogen, the auto and para. If you are measuring at higher temperatures, then it's different. At higher temperatures, auto and para start to behave more closely, and if you are at very high temperatures, they are basically the same, and also they can equilibrate easier. But for Uranus and Neptune, temperatures are very cold, hydrogen is going to behave very, very different, and you are going to have a particular thermodynamics that makes even defining an adiabat difficult, because to define an adiabat, you need to know the specific heat, and this specific heat depends on which amount of hydrogen, how much ortho and para hydrogen you have. If you have an equilibrium at a particular temperature, which is what you would expect, you would have something that is a very weird behavior of this specific heat with temperature, and that is going to affect the vertical structure of your atmosphere. If you have a thermal profile like this, and you say this is close to an adiabat, and you want to extrapolate downwards and study what is coming below, and see what is happening with these deep clouds, dark clouds in the dark spots, you need to understand which kind of hydrogen do you have and what is its specific heat. That is difficult. You want to go deep into the atmosphere, you are going to condense different species. Each of these different species is going to release latent heat, and so your vertical gradient of temperature is going to depend on how much latent heat you release when you condensate different volatiles. The first one that you are going to condense is this exotic molecule made by 2 atoms of hydrogen and sulfur, hydrosulfide. It's methane above, and then below the upper clouds that you are able to observe, this hydrogen sulfide. And then even below, you're going to have a mixture between hydrogen sulfide and ammonia. You're going to have a mixed cloud of ammonia hydrosulfide, and then very deep in the atmosphere, water. And water is very important because the latent heat of water is very, very large. It's 5 times larger than the methane, and it's going to change things. But we don't know what is happening here because our observations remain here. And this plot tries to show the differences in the thermal structure of the atmosphere that you can have at different depths. And this is going to change the behavior of the atmosphere in very specific ways. If you want to study these clouds at different layers, you can do thermochemical models of the atmosphere. The classical formulation is in this great reference by Susie Latreille and Mike Wong in Space Science Review. There have been many different papers studying this and many different approaches. And you can see here a kind of calculation of how your thermal profile is going to be if you follow an adiabat modified by by condensation of the different volatiles. You condense methane above, hydrogen sulfide below. This is probably the layer that we are observing with the dark spots. Then you are condensing an ammonia hydrosulfide cloud, and then a very deep water cloud with ammonia dissolved into it. And because these condensators are heavier than hydrogen and helium, the atmosphere, the kind of this abundances of volatiles, this is methane abundance here, measured in this mixed temperature in the lower axis, here in the horizontal lower axis. This profile changes here abruptly because you are at the highest temperature and methane cannot condense anymore. But you have these sharp gradients of composition, and this is going to change the molecular weight of the atmosphere and the static stability. When we observe the planet, we can sense it, the thermal infrared here, the photochemical phases. In the near infrared and the visible, we are sampling these layers. In the millimeter of radio, we are sampling these layers, and we are seeing a structure here at these depths of tens of bars. And we want to understand this with higher spatial resolution data. This changes completely depending on the amount of volatiles that you have. If you have a planet with an abundance of 20 times solar abundance of the different condensators, your model of the atmosphere will be like something like this in terms of the clouds and condensators that you're going to have. But in terms of the molecular weight of the atmosphere, so this is pressure, you are going to have a light atmosphere above, and then it's going to change. And you see that the density of the atmosphere is very different, not only because you are deeper in the atmosphere and have higher temperature, it is different, especially because here you have lots and lots of water, and you have a different molecular weight, and this provides a complete different characteristic of the static stability of the atmosphere. And so here, this is the Brun-Väisälä frequency in this axis here, with high jumps in static stability whenever you are close to the condensation base of each of these clouds. But if you have even higher abundances of volatiles, 80 times solar, which is possible, we don't know if it is from 20 to 80, your atmosphere is going to have much more abundance of condensates. Your clouds are going to have deeper cloud layers. The density of the atmosphere is going to be very different. And indeed, this stabilizes the atmosphere very much. You are able to have differences in condensables in their abundance at different latitudes. There is evidence of that in maps in the millimeter and radio wavelengths like these ones. And so your atmosphere is going to be very complex because you are going to have different abundances on different locations. They are going to change the vertical gradient of the winds. And you may have something that is very complicated, in which sometimes you can have some moist convection, sometimes you cannot because of this strong stabilization effect. And things are going to be very complex in this atmosphere that we are observing mainly here, and which we want to observe deeper in the atmosphere with higher spatial resolution detail and with higher cadence. So we need better data sets to understand these planets. One thing I would like to say is that even with the gravity data that was obtained by Voyager 2, as the Voyager 2 passed by these planets, the distortions of the gravity produced by the planet were measured by the spacecraft by change in its trajectory. And so from those gravity measurements, you can constrain the interior of the planet. And some papers use that information to try to constrain how deep the winds go into the atmospheres. And the base analysis is from this paper in Nature by Yochai Caspi and collaborators in 2015, in which they predict that the winds in these planets are going to be with a depth of about 1,000 kilometers, shallow winds. And this is important because it will be like 2,000 bars in Uranus, 4,000 bars in Neptune, sorry. And this is about only 20% of the hydrogen and helium envelope, but it's close to the level that you would expect if you were to have very high abundances of water. And so all of these elements are related. And also you would have their different density of the atmosphere because you are having so much water. So we really need to go to these planets and measure the gravity better. And you can only do that from an orbit. And of course, in these planets, there is something very unique that happens. If you have the compositional gradient in the molecular weight of the atmosphere that is so large as we have seen in the previous plots, then the vertical motions of the atmospheres can be prohibited. Normally, when you have moist convection, what you have is some amount of wet air that goes up. As it goes up, it cools. Then, because it cools, it saturates and then it releases latent heat. And so it goes up because although it is cooling as it goes up, it is cooling more slowly than the rest of the atmosphere, and so you can have moist convection. But in these planets, when you release latent heat, your atmosphere is able to have even more condensables. The condensables are very heavy, and so you can inhibit the development of vertical motions. And this happens when you have a critical amount of condensables that are heavier than hydrogen helium. And you can have that in the methane cloud, which is at levels where you can observe. You can have also that in the hydrogen sulfide cloud because latent heat of hydrogen sulfide is very small. You can have it in ammonia, and you can have it also in the water cloud layer. And so there are, even though you can have very deep cloud layers, here very, very deep, moist convection is totally prohibited here because of this sharp gradient in the molecular gradient. You can have moist convection at the deep layers here, but not at the lower part. And you can have a very mixed situation in general, because this is going to be a very complex problem. And this inhibition of moist convection is going to produce also sharp changes in temperatures in these atmospheres, depending on the model that you want to use or the model that you want to play with. And this is going to change the density, the gravity, the behavior of the atmosphere, how you communicate condensables from one deep cloud to another. So lots of interesting physics going on in these planets. To study this problem, you need to take into account which is the latent heat of the different condensables that you have. For instance, methane, which is in the upper clouds with 500 kilojoules per kilogram, which is 5 times or 3 times, 4 to 5 times less than water. And then you also have to take into account the molecular weight ratio between the condensable and the hydrogen helium atmosphere. And so this tells you basically that it's easy to avoid moist convection in methane in these atmospheres, and this is something that is going to happen close to the methane cloud base. It's very easy to inhibit completely convection in this hydrogen sulfide cloud because the latent heat is strong, but the molecule is very heavy. Ammonia is going to be easy to inhibit, and water is also going to be easy because water is going to be very abundant at depth, and so it's easy to avoid moist convection from water at And this kind of inhibition of convection is something that is going to happen in any atmosphere with hydrogen in helium and high abundance of condensators. And it will happen also in atmospheres like Jupiter or Saturn at depth, if they were to have enough condensators. But in Uranus and Neptune, we can study that because methane in the upper cloud is going to be close to this level, critical level in which moist convection gets inhibited. And so here we can study observationally physics of this inhibition of moist convection and what are the observational effects. Do we really observe these kind of sharp changes in temperatures if we can go inside the atmosphere with an atmospheric probe, or if we can measure this from a spectroscopy from an orbit, or are we not going to observe anything like that? And the inhibition of convection really produces something that is, let's say, with changes that are more diffused, or are we going to have these kind of effects in a more complex way? We can have different kinds of vertical motions because we are having active clouds in the methane cloud that we are observing in both Uranus and Neptune, but we don't really understand how deep these vertical clouds stand, how deep they go, which is their activity, if they are truly convective or if they are more condensing clouds in places in the upper layers, far from the deep layer, from the base of the cloud where we expect to observe this inhibition of moist convection. So it becomes important to study the dynamics of storms, moist convective storms in Uranus and Neptune. And these are some candidates to moist convective storms in the atmospheres of these planets, active clouds that appear in certain periods of time in which the clouds are changing quickly in time, in which you can also develop tails like you have here a moist convective storm and you have sonar winds and this storm is moving in this direction and you have different winds here, you can have this elongated tail and you have this kind of motor convection here, but it's not clear that these are very powerful storms because we are not seeing a lot of vertical activity, but also because the observations doesn't allow us to study correctly the characteristics of these features. So these are possible moist convective storms that we have to study better to understand if they are truly convective or not. And of course, we have to study with new telescopes, new observations. In Neptune, these are other candidates. You can have this kind of active clouds in the center of dark spots, which change in questions of hours. You can have these large systems, but these are very high in the atmosphere, observed in adaptive optics in wavelengths in which we are sampling mainly the upper phases. We have a polar wave in which, close to the pole, in which here the winds are producing some kind of instability. Here we have lots of changes regularly over years, and we are not sure if here we have vertical motions and moist convection or not. And also we have an important paradox, and it's that in Neptune we have better inferences of moist convection. In Neptune, we see lots of methane in the upper atmosphere above the tropopause, and that requires moist convection to overcome the tropopause and communicate methane to the upper layers beyond the core trap of the tropopause. And we have lots of clouds activity and lots of variation. But in Neptune, we have very few little candidates of moist convection that we can really study. You see a lot of candidates here in Uranus, and there are not really many in Neptune. Whenever you study one of these cloud features in detail and you do the analysis of radiative transfer analysis to study the cloud tops, you see that most of these features that you are observing here are very high in the atmosphere. They are high phases that are not easy to prove could be related with moist convective storms. And so this is the paradox, and this is the thing. We don't find concrete, specific, good, and validated examples of moist convective storms in Uranus and Neptune. So these are unique atmospheres. They have these extreme seasons in duration, differences in illumination. They're going to affect mainly what is happening above the tropopause in the distribution of phases. Also, the amount of condensation nuclei that can change there. We have extreme winds, even though we have low energy input. These extreme winds change very, very slowly from one latitude to the other in a smooth way. So they are unrelated with the visible bands. And we have vertical seas in Neptune. And you see that although the winds change very smoothly from one latitude to the other, in Uranus there is a lot of variation of cloud activity at different latitudes. And these are very different to what happens in the giant planets Jupiter and Saturn. We have a very rich meteorology at the visible cloud layer, which is mainly based on methane clouds, and we don't understand those very well. We observe candidates of storms, convective or not. We have dark vortices, white companion clouds, atmospheric waves, lots of different things. And in both planets, we have an extreme abundance of heavy condensators that we are not able to really constrain. They could be 10 or 30 times higher when compared to Jupiter and Saturn, 20 to 80 times higher when compared to the solar abundance of heavy elements. And this means that these atmospheres are in this particular regime in which convection can be inhibited at different depths, and this is going to change how the atmosphere is behaving in a larger scale. And we have these vertical extended multi-layer deep weather layers that are going to be much more complex than in Jupiter and Saturn. With the current observations that we have, we can study the planet at different altitudes. This is a spectrum of Uranus that has been transformed into the sampling level that we can observe at different wavelengths. If you are observing in the 400 nanometers, you are sampling basically the 1 bar level. If you are observing at different wavelengths, you can go deeper into the atmosphere or remain high in the atmosphere. When you observe in the adaptive optics in J band and H band at 1 to 2 microns wavelengths, you are sensitive to things that are very high in the atmosphere, above the tropopause. If you observe in the radio and in the millimeters and centimeter wavelengths, you can go to 10 bars depth. But what we are observing in the visible and near infrared is things that are happening in these places and in this methane cloud. In the immediate future, we can observe these planets with the James Webb. And here we will have new windows that I will be speaking about very, very shortly. And in a few years from now, we will have the European Large Telescope, another 50-meter size telescopes with fantastic adaptive optic systems that are going to change completely our capability to study these atmospheres. And even though those telescopes are going to produce a complete revolution of our knowledge of Uranus and Neptune, I would argue that we still need a space mission to understand what is happening in the depths of these atmospheres. And so I will be speaking about some orbiter and probe concept missions to go inside the atmosphere with a probe, measure what is happening there, but also observe from the orbit to really use that probe, that thermal profiles, and those measurements at depth as a ground truth in which to understand what is happening in the planet. Here you can observe spectra of Uranus and Neptune in the near infrared up to 5 microns in the left, and in the thermal infrared from 6 microns to 28 microns. And these horizontal lines correspond to different filters that are available in the James Webb Space Telescope that are going to sample different depths of the atmosphere, because this light is observed in the atmosphere at different depths. And Uranus and Neptune we can observe in all of these filters with the NIRCam camera and with the mini instrument in the mid-infrared. And so if we observe in different filters, we have different absorbing bands of methane and hydrogen, and we can study what we are observing at which depths we are observing. And we can also observe with spectrometry at very high spatial resolution. With James Webb, the spatial resolution is a little bit better than Hubble, but not better than twice. So we are going to get images of Uranus with only 120 pixels for Uranus and about 80 for Neptune, but that is going to be much better to what we have now. And with image reconstruction techniques, we can improve a little bit over that. And of course, if you observe a complex planet with a new telescope like the James Webb, you are going to observe new things. On the right, you see the first observation, the first science observations of Jupiter from an observing program. And this is an error-release science program led by Inke de Pater at Berkeley University and Thierry Fouché at the Observatoire de Paris in France. And this is one of the first images that has been released in which you are observing new things: hyperhaces, lower clouds, the great spot, convective storms, an elevated limb that should not be illuminated by the sun. Here, this is completely new. And of course, lots of other different details, like the rings here. But in terms of the atmosphere, this is an image that is very rich. And actually, this is close to the spatial resolution of the observation, but you can zoom in and see gravity waves all around this region, very high in the atmosphere at the layer that we have never observed before. Although these kind of gravity waves have been observed before in Jupiter at lower levels. And here, this is a cyclonic system. And you have all of this train of gravity waves. So even in a planet that is much better known Like Jupiter, we are getting new fantastic results with a telescope like JWST. And JWST is going to completely change what we know about Uranus and Neptune in the next few years, and it's going to really change the field of view, our understanding of these planets. But in a few years, with these new 30-meter telescopes with multi-conjugate adaptive optics, we will have new capabilities to observe these planets. So the ELT with an instrument Ricardo and with an adaptive optic system called Maori will be able to obtain images of Uranus and Neptune at a spatial resolution of 20 kilometers per pixel or 33 kilometers per pixel. At these spatial resolutions, Uranus would be an image of 2,500 pixels wide, better than the observation of the James Webb that I saw it before for Jupiter, and 1,500 pixels for Neptune, which is much, much better than any Voyager observation of Neptune. And of course, with better spectroscopic resolution, with a multitude of filters from 0.8 to 2.34 microns, about 30 different filters in which you can observe at different depths of the atmosphere. So sensitive to what is happening at the methane cloud, at different layers of the methane cloud, the upper part in which we are observing these atmospheric features, the lower part in which we have this transition in which the atmosphere is not allowed to really work with moist convection, but maybe we have some moist convection depending on which is the local abundance of condensates surrounding the locations with more abundance of condensates. And so this is going to completely change our view of these planets. These telescopes with 50 meters and these adaptive optics are the telescopes that will put Uranus and Neptune to the level of knowledge that we have for Jupiter in the near future, in 5 years from now. So here I'm comparing one observation of Voyager 2 of Neptune, the greater spot at 50 kilometers per pixel, with the optics of that camera and the instrument that it was available there, a Vidicon instrument similar to the television camera of the 70s. And the typical spatial resolution of a Junocam image of Jupiter at 30-40 kilometers per pixel. And of course, you can see that if you get to this kind of spatial resolution, you get to new physics, you get to the capability to really understand what is happening there. So the ELT and other 30-meter size telescopes are going to completely change our view of these planets, both Uranus and Neptune. But as you may know, NASA every 10 years makes a full study of the different areas of research where the space agency wants to develop its main science projects. And in the last decadal survey released this year, earlier this year, NASA has declared Uranus as the top destination where to develop a dedicated flagship mission, a very expensive mission with capability to develop an orbiter and a probe mission. And of course, there is a strong interest on ESA member states and other countries to participate in such joint mission, and many different researchers moving on to try to be able to participate in that mission, with many white papers published over the last 4 to 5 years. If you look at the literature, you are going to find lots and lots of reviews of Uranus and Neptune in the last 3 years because of that, because the science community in planetary science, in giant planets, in solar system formation, and in exoplanets believe that Uranus and Neptune are very interesting topics. And Uranus is easier to study from a spacecraft point of view because it's closer and it's easier to arrive there. And there's one opportunity to develop a mission which could be launched in the early 2030s that could approach to Jupiter using a gravitational assisted maneuver to arrive to Uranus very, very soon, only in the 2040s. Which is still feasible for the people that are trying to move forward these missions and to do the science. And of course, this is a very exciting period, especially for young people, that we certainly be able to see these missions coming on. If we lose the launch opportunity in the early 2030s, we will not be able to arrive to Uranus and Neptune until 2050. So only young people today will be able to do the science of those that those missions promise. And that science is very important. If we are able to understand the dynamics of hydrogen atmospheres, we have the link between what happens at depth in the lower parts of Jupiter and Saturn and what happens in the exoplanets. We can refine the models of evolutions of the ice giants. We can understand how these planets form and how the complex atmospheres are working. And it is in Uranus and Neptune in which the topics related with the planet formation and the behavior of the atmosphere are more tightly connected because of the importance of these high abundance of volatiles. So I think that I will stop here with the idea that I have tried to convince you about the importance of these topics, and that we are going to see a whole revolution in our understanding of these planets in the next few years. But we really want to go there to really understand what is happening at the deeper level. At the deeper levels. And with this, I finish this talk, and I remain open for the questions that you want to make. Thank you. Thank you very much.